Thank you for joining our webinar today. With me are your speakers joining us from Ireland, Darren McHugh and Girish, and I hope I said that right. I think it's dinner time for them, so thank you both for taking the time to make this webinar happen. My name is Julie Chen Nguyen. I will be your facilitator. We will have a Q&A session in the end. So at this time, I'm going to turn the floor to Darren McHugh, your senior product manager from Innopharma Technologies. And then after Darren, he's going to pass it over to Girish, which is the senior software developer who is very familiar with AI, machine learning, and the topics of CNN. So go ahead, Darren, please go ahead and turn on the audio and share the screen.
No problem. Thanks, Julie. Okay, it's great to be back invited for another one of these webinars. It's funny, I think it was like over a year and a half ago, I did a webinar with Jeff about image analysis. And I remember at the end of that webinar, I kind of alluded to where I thought image analysis was going in the form of machine learning. And I'm delighted to be back now kind of presenting on machine learning and a product we've developed in-house and are offering for our particle size technology with the Eyecon 2. So yeah, it's just really kind of showing the journey we've gone through in just a short time of a year and a half of being able to take something really from which was a concept and something we were, let's say, sandboxing back then to now being a fully fledged and launched product for us. So I'm going to start off talking a little bit of, well, I guess, background and introduction about us, a little bit about how our technology works with image analysis and talking about how it works traditionally with image analysis. And I'll start to go into a little bit then about how that's leading into machine learning, but then I'll hand it over to my colleague Girish, who will take you along the journey of what we've developed using machine learning with convolutional neural networks. And I'll come back at the end for a bit of a wrap up, and then we'll go into a Q&A. So a bit of a mandatory background introduction, really, just kind of so you know who we are and what we come from. Innopharma has been around for over 10 years now. Our very first technology is a image analysis based technology, the Eyecon 1 for particle size and shape. So we have over 10 years of experience of working in that space, predominantly in the pharmaceutical field, but not exclusively. But the company as a whole has evolved into 3 different divisions. We are now Innopharma Education, who offer courses in the life sciences and med tech industries for people looking to get into that space right up to master's level. Technology, which is who we are. We offer high-tech solutions to people working in pharma or med tech or those types of industries, and also our technical services division, where we offer engineers and for people in the field for validation and services such as that. We're an Irish company. We're based out of Dublin, Ireland, and we have over 120 employees, and we're still growing, which is great. So let me get into Innopharma Technology and what we're talking about today with image analysis and machine learning. For us, that's all focused around our Eyecon 2 technology, the particle size and shape analyzer. But this really just gives a bit of a snapshot of our journey of all the products we've developed over the years and what's kind of going on with the company as a whole. But if I kind of just drop this line in here, it really shows we started our artificial intelligence journey really toward the end of 2020 and going from proof of concept using off the shelf, let's say, models to now developing our own models and deploying a product that we can offer people where they can use machine learning image analysis for automated particle size and shape detection. A bit about the hardware itself. At the base of it, it's a vision-based technology. It's non-product contact. What we have here is a robust industrial camera system that's suitable for the pharmaceutical market, being GMP designed. Its software is 21 CFR Part 11 compliant. It's an ATEX rated device, so meaning it can be used in potentially hazardous environments as well. So a very industrial, rugged camera system is what this boils down to. And that's our hardware that we use for ascertaining these images that we're going to talk about for the image analysis. Small particles are a big deal in the pharmaceutical industry. Millions, multi-millions of dollars a year are spent on research and development, on quality control, on modifying the size and shape of particles, because it affects everything in the manufacturing process, upstream and downstream. And what I mean by that is powders require certain sizes and shapes to flow well from process to process without things like segregation happening, attrition happening, where they're breaking down again, maybe before they get to their final stage. And so that all affects things like quality, or let's say if we're talking about drug products here, it'll affect things like dissolution rates of those drugs. So the rate that they get absorbed at in the human body, and affects things like bioavailability of those drugs. So hence there's a lot of time, effort, research, and expense invested in modifying particle size and shape. So we're looking at different configurations here on the left of the ways that you can use different sensors and technology on the process. And when we look at these, we talk about them being used to measure things at the line, or off the line where it's sent away for analysis, or on the line where it's bypassed to a sensor, or in the line, which is predominantly where we target our technology to measure where the particles are being modified. So you can get those images at the location where they're needed and make decisions about your process, be it for quality control or modify a setting on your process to save the product or batch, for example. And on the right is an example of a manufacturing line. This is actually a solid oral dose manufacturing line, which would be very typical for tablet manufacture. An example of where you would use an image analysis device for all these different steps along that journey. So if we go a little step closer now, rather than an overview of the industry, we're going to look at the hardware just for a slide or two. The Eyecon 2 uses a camera system with a front lit illumination source of red, green, and blue LEDs. Essentially, all vision systems have to meet a certain criteria of ascertaining images that are well focused and well illuminated. That's really what you need to start your image analysis before you do anything. You have to ascertain you get good quality images. So be it a different vision system that you use, you have to make sure your lighting source is correctly illuminating the product you want to grab an image of. And I'm sure we're all familiar with using our own camera phones, for example, of taking a poor quality image that's either out of focus or poorly illuminated, maybe where the sun is behind you or in front of you, in fact, for taking an image. The same things apply to grabbing images of particles as well. So what happens is material passes by our camera system, the red, green, and blue LEDs pulse, illuminate it, and an image is grabbed at the same time. And the image on the right is a raw image taken from the Eyecon 2, showing that crossover of red, green, and blue LEDs, which we use for in our traditional image analysis for edge detection. And that's how we can then see the edges of these bound particles that we can then ascertain their particle size and shape, which I'll get to in a moment. There's lots of other different methods out there, not just this method of direct illumination with our camera system. There is other methods for determining particle size and shape, aside from image analysis, such as laser diffraction or even sieve analysis, the oldest method in the book. And it's just to point out at this point that there is many different ways to measure particle size and shape, and it's not a one size fits all. I'd highly recommend HORIBA's particle guidebook here, the 2022 edition. It's really a great resource of talking about all the different particle size methods that are out there and differences between them, as well as it gives a breakdown of particle size distribution. And I don't think there's any better resource out there for describing what's the difference between volumetric measurement and numeric measurement, for example. So anyone who's working in the space of particle size and shape, I recommend that. It's a good read. So image capture. So if we get down to the image analysis a step further and we talk about particle size, we can see in the middle here, we have three images of the same particles. The raw image at the top taken from our Eyecon 2 system with that crossover of light. And what's traditionally done in image analysis then is the area of those irregular shapes is either worked out via methods of thresholding or binarizing the image, converting it to black and white. And that, let's say, black versus white background is subtracted from each other to work out the area But then to process that into a volumetric measurement, you project a equivalent spherical diameter of that area, and that gets converted to a sphere to work out volume, just using some simple mathematical equations in the background. That's the way all kind of particle size and shape image analysis systems work in terms of working out volumetric measurements. The Eyecon 2 does the same, only it takes an extra step of adding an extra axis. So it takes a major and minor axis for matching the particles. So the longest chord length compared to the shortest perpendicular chord length. And that's your major and minor axis for an ellipse. And that ellipse then gets converted to an ellipsoid to work out volumetric measurement. And that's just the industry standard, the way things work, using Ferret's diameter or Martin's diameter and projecting an equivalent sphere for that area that you see. And this is just showing then, like, in a 3D plane, if you were to grab an irregular shape, match an ellipsoid to it, you would take the major and minor axes, take the average of the two of them for a prediction of your third dimension, and that's how it takes a 2D image, let's say, and projects it into a 3D measurement. Alrighty, so quick snapshot then of what the EyePass software does for image analysis. This is what the user sees. On the left, we've just images coming in from the camera system, like a live feed of these images. So it's a real-time system in terms of the data it reports out. And then the charts you're seeing here, the green, orange, and blue, are your D values, your diameter values for D, and a snapshot of D90, 50, and 10, which is your particle size distribution for all these individual particles that you're seeing on the left over time. So there's thousands and thousands of particles getting measured with this system automatically and digitally. So that's the user interface, designed to be user-friendly and simple. After that, you can export that data in the form of a PDF. It's nice and formatted, again, giving you a snapshot of what was recorded from your images for the particle size distribution. But you can also go a layer deeper and export all this data here in the form of a CSV file. So every line you see here is an image that got analyzed by the EyePass system. So for every image it analyzes, it outputs a full particle size distribution, all the way from D5 to D95, which is, anyone familiar with particle size distribution, that's high resolution compared to something like sieve analysis. You're actually getting the full distribution here. And this is a line of code for every image that's analyzed. Okay, that was me just giving the intro to us, the technology, a little bit of setting the scene of the way our tech works and what we're interested in terms of image analysis and how you pull out the features of interest, such as particle size and shape, traditionally, and what is accepted by the industry to date. I'm going to hand it over to my colleague Girish, who will take it from this ground setting over to more about machine learning image analysis and how that works, taking images from the Eyecon 2 camera and processing them through a machine learning method.
All right. Okay. Thanks, Darren. So yeah, just to summarize what Darren just explained. So this is our Eyecon/EyePass system. So EyePass is the software component which drives both image acquisition and image analysis. So you have the camera. It's presented as drawn as a schematic here, and the data comes in and is analyzed in the image analysis component. So just to dive in a bit deeper, what is image analysis? Just as the term suggests, you just analyze an image to extract some kind of data that's of interest to you, or depending on the problem. For particle image analysis, that could be the major and minor axis length of every particle in the image. So the image would go into the analysis system and would get these data out of the system. So pretty much it reduces an image to a set of measurements that are of interest to us. So at a very high level, we can segregate or divide the steps involved into two broad tasks. One is a vision task, where the algorithm or even the human observer has to look at the image, perceive the image from a visual sense, and make sense of what's there in the image. So for particle size measurement or anything that has to do with measuring something about an individual particle, that could be delineating an object of interest or every object of interest in the image. So for example, the system could draw, or we could draw around a particle here. So that would be what we would need to do as part of a vision task. Then the second task would be a measurement task. So once we have identified the object of interest or all objects of interest, we would measure the necessary attributes of the object. That could be, for example, major, minor axis length, or even the particle size. So then for the major minor axis length, we would approximate that to an ellipse and make the measurements that we need to. So if a human observer was doing this, the vision task would be pretty much straightforward. We don't even have to think about it. We can actually see the edges of every particle here. And we don't even, if we were to do this, perform this analysis, we wouldn't even have to draw around the particle. We'd simply be able to measure the major and minor axis length without even having to delineate the particle. But the measurement task, if we had to do this for a number of images, a number of particles in each, that becomes tedious and frustrating. So that's why we would design algorithms or systems, computer systems that would do it for us. But for computer systems, the level of difficulty is the opposite, because the pixel that are in the image are pretty much just numbers. All the computer sees is a set of numbers. Then it is tasked with perceiving these numbers or making visual sense of these numbers. So that's pretty much the computer trying to emulate human vision, and that makes the vision task extremely challenging for machine vision systems. The measurement task, on the other hand, once we have objects detected, it's straightforward, it's well defined. So for most image analysis systems that are designed, most of the work is in designing or implementing the vision task. And this specific task of delineating objects of interest, it's called image segmentation. And the quality of segmentation required the goal or what is acceptable or not is defined by a human observer. So this, the image on the right-hand side that you see, in which every object of interest is colored using a different color. So that indicates that every particle here is considered to be unique or separate from the particles surrounding it. So that's set by the user, that's defined by a human observer. Traditionally, which is what we do in IPAS version 2, many years before supervised learning or convolutional neural networks or deep learning took off, the classical image processing techniques were used. And this slide here shows one of the simplest technique for segmentation, which is look at every pixel's value, and we define a threshold and say any pixel value which is beyond or below the threshold value is an object or background. So if you look at the intensity distribution of this image here, you see the brighter particle pixels, they form this peak on the right-hand side. They have higher intensity values, and the darker pixels in the background, they form a peak here on the left-hand side. And the thresholding algorithm simply works by defining a threshold, trying to separate those two peaks. But this not every image has this well-defined peak, and even when it does, the results may not be acceptable. So in this case, in this example, we see that the edges of the detection don't align that well to the actual edges of the particles, and we also have some false positives, tiny noisy specks that are picked up as particles. That's the simplest technique though, and it's not used that much. Another well-known technique is called the watershed algorithm. So what this does is it takes the analogy, it looks at the image as a topographic map. In other words, it looks at the intensity values, and in this example here, the brighter pixels from the particles are drawn or looked at as a valley, and the darker regions from the background are looked at as peaks. So it takes an analogy from, so what it does, it floods the valleys with water. That's the analogy it uses, and it keeps flooding those valleys until flooding any further would join those two regions. So the watershed, the name comes from the fact that the ridge separating those two valleys from the flooding is seen as the edge that separates two regions. So that's just an analogy for the algorithm, but the results, for example, could look like this. Now we see here that the edges still don't conform to the actual particle edges, but technique does get rid of some noisy detection. There are fewer false positives here. Then there are machine learning techniques that were used even before deep learning. There are unsupervised machine learning techniques which cluster pixels based on similarities. So this, on the right-hand side, we see these pixels here mapped into a color space. In this case, it's the RGB space, and clustering techniques would group these points, and based on similarity or how close they are to each other. So it would automatically find groups within that distribution. And mapping that back to the image, then you can see it performs slightly well in terms of the edges. They're closer to the actual particle edges. We still have some false positives in terms of tiny specks here. So coming to then what's been used in most of computer vision problems, including image segmentation, are convolutional neural networks. So these are also called deep convolutional neural networks, because typically the internals of these networks have multiple stages, or deep stages, or deep layers. So it's just a schematic that shows what is typically extracted when an input image goes into a network. So the system is trained to extract features from the input image, and these features, these could be edges, vertical lines, horizontal lines, or bends, anything, and these features are then grouped as the image passes through the network, and there are multiple such layers inside the network. So depending on how it's trained, the network learns to extract features of interest and to give us the output that we want, as defined by a human observer. And this is the output using one of these systems here. And we can see how the edges closely match the actual particle edges, and even including this small particle here, which is partially occluding a larger particle behind it. It also, this image here that we see, it's the raw output straight from a trained neural network, a trained model, and we see no false positives on an image like this. Just to look at what's involved if we were to design algorithms using classical image processing techniques, or even classical machine learning techniques, typically we start with a set of images that's defined, or these are representative images that the system should be designed to should be able to analyze or segment. Apart from the core segmentation algorithm that's used, there's also a lot of pre-processing steps that's involved, and post-processing steps that are involved in generating output that's acceptable. So a lot of effort goes into designing these. So we have to design a full pipeline that takes in the input image, does some pre-processing, performs the segmentation step, and then post-processes the output of the segmentation to remove false positives, or any sort of post-processing to refine the segmentation output. So once we develop a system for this, then it will be used on the field to analyze images that the system has never seen before. So as I mentioned, a lot of effort goes into creating this pipeline in the first place. But if we want to go back and support a new material, or not even a new material, even images of the same material which are visually different from what the images that were used during the design, we typically find that significant modifications will need to be made to the pipeline. And more often, you just have to come up with a new pipeline or new set of steps to cater to the new material or images. So it's a lot of time getting something out of this process. On the other hand, when we go with convolutional neural networks, a lot of time spent on creating data sets. So data sets are typically, we start with images. Again, these are images we acquire from, say, our imaging system, the Eyecon 2, and then a human expert spends time labeling or annotating these images, defining every particle's edges, and that constitutes the data set, the image plus the human labeling. So this data set is then used for training the convolutional neural network. So the training process helps the neural network learn what the internal parameters of the network should be for the mapping that we want from the input image to the labels that are defined by the user. And once we have a trained model, as we call it, it's deployed, and a deployed model would have all these parameters set, and then that can be used to analyze any image, and that we get an output. So that process is called inference. So typically in practical situations, we see that there are not enough images to form a data set of acceptable size. I mean, we could have a lot of images captured from the imaging system, but we may only have a subset of it labeled by a human expert. So if we have, let's say, 20 to 50 images where a human observer has labeled it, we could find that these are not sufficient to train the network. So there's also usually a step performed called data augmentation. So in this step, what we do is we take those original set of images and the annotations, and we modify them, transform them. So these transformations could be anything like cropping the image or flipping it or rotating it. And these then form a new set of images, which then get added to the data set. So in other words, it augments the data set. It increases the size of the data set. So we have a larger set of images to train the network with. So that's just an overview of what goes on in developing a model and deploying it. And then the training, just to go a bit deeper into what exactly happens during a training process. We start with the data set, and a really statistical method that we use for estimating the skill of the model is called k-fold cross-validation. So at the outset, when we have a data set, we keep aside a certain percentage of that data set as a test set. So we keep that aside. We don't use it for any of the training steps. We keep that aside. We only look at it at the end of the process. So we look at it as data that the network or the model has never seen before. So when we measure performance at the end of the training process, we truly measure what the performance of the model would be on images that it has never seen before. So we keep that set aside, and then we are left with what's called the training set. And we could use the whole training set to train the model, but what's done as part of k-fold process is we divide the training set into k-folds. This example, it's 5, so there are 5 folds in the training set, and training is performed in each instance using 4 of the folds, and we evaluate the model on the remaining fold. So this is done because there are certain settings in the network that have to be tweaked as part of the training process. And by keeping aside a portion of the training set as a validation fold, as it's called, we can train the model on the subset of the training set and evaluate the model on the validation set. And we can then see if the configuration of the network is good or not. And when we do that, we keep doing that until we tweak the model to get the performance that we want. And we then pick the model with the best performance, after changing the settings of the model in different ways. And once we pick that model, then we measure the performance on the test set, and that is what we use as the model's generalization performance metric. So that's how we would do a typical training process. Just to summarize what we currently see with the version 2 of IPAS, which uses classical image processing techniques. This is the output of the segmentation algorithm that we have currently in place in IPAS v2. Now, granted, there's post-processing steps that take place to refine the segmentation, but this is the raw segmentation output, and we see that the edges are noisy. It doesn't conform to the particle edges, and there are noisy bits that are detected around those as well. And by using, in IPAS v3, by using convolutional networks, we see the output that we saw earlier, which is much cleaner, and we can even deal with partial occlusions here. So that's pretty much from me. I'll hand it back to Darren to go a bit further into how IPAS v3 compares with IPAS v2.
Right. No, thanks for that, Girish. That was good. That's taken us really from what the Eyecon 2 is, what particle size and shape is to the industry, why it's important, and how we use image analysis to gather that information. And then we've kind of gone on our journey of talking about classic image analysis and how that works, and then basically how the new artificial intelligent method using machine learning, specifically using a convolutional neural network with supervised machine learning, and how that can improve your image analysis. So that's what kind of happens in the background, all the work we've done, let's say. And I'm going to kind of talk about the results of that work and what the user sees. So the user experience, if anyone's familiar with our technology, IPAS version 2 on the left here, is when you set up a configuration, the steps that are involved for setting up your camera system, basically setting up its illumination, its focus, and the settings that the image analysis uses for determining your particle size and shape is on the left. So that's our classic image analysis model. The version 3 of the software, as you can see on the right, looks very similar, but you just now have an option to select the artificial intelligence version and pick a model that might have been developed for your material type, and use that model in a real-time image analysis setting for particle size and shape. So that's what I'm showing on this slide. So if we look at some results before and after machine learning, on the left is version 2 of the software. And what we're looking at in this image area on the top left is actually glass beads. Because of our front illumination method, there's a lot of reflection from something like glass beads. And if you're able to maybe squint at your screen, you might notice the red, green, and blue LEDs from our camera system are being reflected back from these glass beads that it's looking at. You can actually see a little ring of red, green, and blue inside each one of these glass beads. That caused havoc for our traditional machine learning method. Our traditional image analysis method, where we used thresholding and a few post-processing steps. So if we look down in the bottom left of this screen, you can see all these green circles, which are essentially false positives that have been matched for particles, or what the image analysis system thinks are particles within inside these glass beads. But let's say me and you know that they're not particles, because we can visually see that they're reflections just from the LEDs. So we would ignore them if we were to analyze this for particle size. What gets reported back, if we look at a snapshot of that, is these green circles are giving false positives. So essentially you can say we're getting these types of results for D10, D50, D90, and as you can imagine, that's junk. That's not being reported back correctly. But if we take a machine learning model that has been supervised machine learning, where we, the human in the loop, have initially did a training set and told the model that these are the edges of the particles that we're interested in. And we built a model from that went through a convolutional neural network, thousands of iterations to improve its ability to match edges of these particles. And what you get reported back then is on the bottom right, these masked images of all these different colors with the correct edge detection, essentially, for each of these glass beads. So what gets reported back then is these D10, D50, D90 values, and that's a winner. Essentially saying that machine learning can do a better job of, after being told and trained what is the feature of interest, to extract that data versus traditional image analysis methods. And then the part of a bigger study, we use glass beads on purpose because they're an industry standard, something that's always been used for sieve analysis to determine if your sieve is correctly operating, correctly calibrated. So these glass beads are traceable standards, essentially. So they're of a known size, and that's why we chose them. So we were able to actually compare what, let's say, the manufacturer's known size of these glass beads is, compared to our IPAS version 3, which uses machine learning methods, and we correlated those results against each other. Anyone familiar with particle sizing technology would know that you always use correlation when comparing different methods, because what we're comparing here is essentially image analysis versus sieve analysis, both of which have two different methods of determining particle size. So we're not looking for a direct comparison, we're looking for a correlation. And a correlation result of 0.95 is really good. It's a strong positive correlation. The trend line's heading in the right direction, really showing that these results are significant to each other, meaning they're valid results. So that was us just proofing out the ability of using machine learning image analysis. And this slide here is really just showing some of the further potential of using this image analysis method. We just put 3 different glass beads of known sizes into the image area, and it successfully detected only 3 glass beads. And you might think, of course, that's what you want. But for traditional image analysis methods, doing something like this is much more difficult. But it's really showing the capability now of using of machine learning. And then we just pushed that boat out a bit further, really, showing different materials, using a general model. So typically with a traditional image analysis method, you might only be able to measure one type of material, or maybe even one particle size distribution, without having to then go back and adjust thresholds for a different color material or a different size material or things like this. This is like a wide distribution of glass beads and multi-particulates and granules, even in the same image area, all being trained in separate models, but then combined under the one machine learning model, and again, successfully and positively, correctly matching all the different materials inside that image area once it's been passed through the image analysis. So really exciting times for the Eyecon 2 and IPAS, having this capability now under the hood. That's about it from me and my colleague Girish. Just here, there's a slide at the end really showing the difference that the traditional image analysis would have matching particles versus the machine learning image analysis. Yeah, thank you.
Thank you, Darren, for the excellent talk. That was a lot of information. I was trying to learn as well, as someone who's familiar with traditional imaging, how that could help people save time by correlating to a very traditional method, if you will, like sieving, that requires a lot of cleaning. Okay, so one question that popped in is, how can we detect particle shape when particles overlap?
I can take that one. Sorry, for overlapping particles, our illumination method of the red, green, and blue LEDs would show a crossover of light of particles overlapping each other. And that still kind of stands true for the machine learning method. So when we're identifying overlapped particles via the supervised learning method, where we're manually telling it where particles overlapped because we can see it, it can then still successfully identify that particle where they're overlapped for, well, first, let's say size, because it does a boundary of its size using an ellipse, and that's then converted into a shape measurement. I think that answers the question.
I think so. Is that part of the also machine learning process?
Yeah, so it's still a benefit of us using the red, green, and blue LEDs and a color camera versus some other camera systems that might use a black and white camera, because you can't tell where those particles are being overlapped. You know, you might have a smaller particle inside the area of a larger particle, and it's still going to look like a black and white background. So using that red, green, and blue LED method still has its advantages of detecting overlapping particles.
And also, is this a software package that can be added on to existing Eyecon 2, or is this a separate package that's only compatible for a newer model?
It's really just a software update. It works with the same hardware for Eyecon 2s. It is so it's a new type of software upgrade. It's also being ran on graphics cards. So our traditional version 2 of the software would run on a CPU, and this is running using a graphics card. So when someone would like to update to version 3 machine learning, we just have to make sure they have a compatible graphics card, because it's, as you can imagine, it's computationally heavy doing image analysis like this. And we've designed it to run on the graphics cards now, which is pretty common in industry.
Thank you. Okay, I think that's about it. On behalf of our group, thank you so much for attending. We will also be at the PowTech trade show in Germany, which I believe the Eyecon 2 will be on site for you to look at and to study and to ask any questions and pick Darren's brain. And it's going to be from September 27th to 29th. All right, we'll see you at our next webinar. Don't miss it. And make sure you join our newsletter by answering yes to the post-webinar survey, or connect with us on LinkedIn, Particle Characterization Group. Thank you so much. Bye, everybody.
Bye. Thanks, Julie.
Thanks, Ron.
Thank you.
Thanks, Julie.